First of all, thank you so much for opportunity to give us to present our work from Micra, and also I'm really excited to present our work that might be closely related to one of basically your tool in Voxel 51. So definitely I would benefit from your tool or the opposite, but I'm so happy that we can discuss later after my presentation. So hello all. Let me, sorry, I had a pop-up here. Okay. So yes, hello all. My name is Dimitrios Chatziparaschis, and I will present you here our work from Micra that basically has to do with on-the-go and multimodal object detection in the field, especially starting from limited data. So let me get to the problem in general and the motivation. So nowadays we know that there is an urgent need for near the ground field monitoring in the fields in order to improve in general agricultural practices, but also to minimize environmental costs and also maximize the profit. One of the ways, basically, such scenarios in the field can be quite laborious and costly, especially when you operate in larger areas. For example, you can see here from the figures on the right-hand side, data collection can be distinguished in many different parts, such as starting from microwave radiometer sensing, from the top image to solar panel electrical conductivity measurements, or even to field mapping. Many of these applications have been pivoted towards robotics in order first to treat this labor-intensive status of them, but also to improve the accuracy of the methods. Uh, so now if we can narrow down in detection, there are many robotic applications applied widely, but if we can organize and distinguish some of the current limitations, we can conclude in maybe three different, basically basic topics. That first, that we might have many of the works being fine-tuned on specific data sets. So in some cases, they might present limited zero-shot capabilities, especially when we operate in similar fields but in different environmental conditions, or we apply in even in different fields. But also, some of the cases, these methods, in order to improve the detection accuracy, they might require on the going how we operate new manual annotations from the operators that can also create some extra work for basically the farmers and operators in the field. But also, many of these methods nowadays, I don't know why it's starting that. Many of the methods nowadays, they are basically based on, trained on single modalities and even in single object detection. So their applicability is not as broad and they have to be also specifically tuned. Uh, so given all this current status on the detection part, one of our initiatives and our work is that we wanted to develop and test out a lightweight annotation detection framework in order to perform on-the-go and multimodal detection in the field, but most importantly, starting with really few data. So specifically in our application here, we tested under vine trunk detection, but this is, of course, this is not restricted to that in the agricultural setting. And you can see also here from the figure on the right-hand side, more like an overview of the general system, how it is basically aparted from. In our case here, we deployed, of course, a ClearPath Jackal with three sensing modalities, image-based modalities, aparting basically a thermal and RGN and an NDVI, basically a near-infrared camera. And of course, we utilized onboard robot pose and capture LiDAR data in order to come up with the accurate 2D and 3D vine trunk detection while on the go. If I can, we basically continuing to the main contributions of our system. First of all, is that gonna go more analytically is that first that we have a development of an early fusion annotation pipeline in order to initiate masks across the diverse sensing modalities. So we can initiate basically the training procedure on the go on our robot. This first module is also interconnected with a second basically point that is a stage incremental detection procedure that one of the main characteristics is that we are detaching from having new manual labeling while we are on the field, as it basically leverages prior knowledge from the already basically captured knowledge from the field in domain in order to refine and improve detection while we're operating on the go. And finally, something that we also tested and it was important for us is that we wanted to make sure that we have accurate in-field vine localization. And for that reason, we employed and included in our framework a model-enhanced LOAM algorithm, agricultural LOAM algorithm. And one of our previous work that has to do a basis of a tree association framework in order to create sparse maps, as you can see from the figure, from the field, from the figure here, that we can also include multimodal information on the go, along with the geo-referenced vine locations while the robot is moving. Let me jump directly more to the proposed framework for this setting. So first of all, given the raw input, as you can see on the left-hand side, our system synchronizes have something with a click here, synchronizes and generate semantic mass across the modalities, the different modalities. So in this step, we just need to note that in the first step, any semantic segmentation model can be used just to initiate the first masks along the modalities. So we can proceed with the first generation of the training set. One important thing here before we create this training set is that we utilize basically we spatial associate these masks generated by combining the interpolating the closest received in time point cloud in the robot, but also using the robotic pose, right? So through that we could actually see that our masks are associated in space, so we were ensured that we create accurate masks and accurate labels for the training set. So given that, since we create this small pseudo-labeled data set, what we do is basically we initiate and we feed this to the training detection pipeline on the right-hand side, as you can see. So this module, what it does is basically it refines basically, it's an iterative method that is a three-step iteration that refines and augments the available data from the training set while being on the go, and requires only an intervention, a small intervention by a human operator only in the start of the training procedure in order to correct some of the part of the pseudo-labeled annotations. So given through the iteration, our backbone basically utilizes or distills knowledge from the previous state and improves its detection capabilities across modalities. I think something I have automated here. And basically improves the training set itself, so it becomes stronger. So as we said before, our method is based on utilization and also synchronization of the different multimodal input. So in order to do that, with the LiDAR points we are getting from each sequence, given the synchronized frames, we are projecting closest to the reference frame. So as you can see, having the projected time, correct projected point clouds and the time synchronized multimodal input, the detected masks that are in the 2D aspect, we already know and we can easily directly assess and lift them to 3D space in order to proceed with the correlation between the different camera frames since we have a calibrated system. As you can see, the cross-reference, as it is cross-reference across the modalities, we can associate matches and we can initiate pseudo-labels for trunk detection in that case. From the last figure, as you can see from the right-hand side, some of the vines might be detected or not detected given the different modalities. So this is why it is important that our system is utilizing early fusion so we can use all the information available and determine if we have an observable vine trunk or not. So building up the detector itself as the steps. First of all, we had a collaboration with our university with the Gallo vineyards here in California, and we deployed our system in the Cabernet Sauvignon vineyards. vineyard fields. In order to build the detector, we first employed, as we said, the segment anything model, but of course we can replace it just to initiate the first set of annotated images. So even starting with a small number of images that we started in that case with 100 images, pseudo-labeled images by the backbone model, the first iteration by the training of the baseline model, you can see that it showcases some promising but partially detected results among the modalities, given basically the current setting. So by utilizing the baseline model, the next step, what we do as a next step is that we include the high confidence pseudo labels during the training set, and we can repeat training. So by doing the training of the new data, we have a resulted model that can improve in accuracy. You can see from the figure C, bringing basically more detections among the modalities, and also specifically here increasing by 60% precision and recall comparatively. Uh, as the next step, because this is happening on the go, is that we wanted to include, since we have also the backbone model, we include new labels, basically new images across all the modalities, and we continue with training the new set of the detector, utilizing also its previous knowledge. So the enriched detector in the end could reach up to 0.83 of precision in vine detection, showcasing directly better multimodal capabilities. And also, as you can see also from the figure D, it might have also the most of the detections. Uh, yeah, sorry for this. I'm not sure how I can disable that. Yeah, so having the 2D detection, we would like to see how we can proceed like in 3D detection part. So big part of our work that I had to do to actually be in 3D detection is based also one of the previous frameworks that we developed that had to do with association of the trees and while we move in space and how we can associate new detections with previous detections already seen. So this framework that we utilized basically employs an entropy-based correspondence method that associates new clusters basically detected in the field by both utilizing the positional data of initiation of each cluster, but also utilizing the characteristics of each tree specifically. I'm just giving more like an asterisk here because I will explain exactly in the next slide what is this characteristics that a tree might offer, more like as an object. So on the left-hand side, basically of the video, you can see how the fusion of the camera, of the frame, and the 3D LiDAR points is projected, and also in the citrus farm case here, how the detections are basically visualized. In our case here, our method was also robust in terms of windy conditions and also in sharp turns of the robot itself. As we said, as I also mentioned before, perfect. Uh, in order to achieve distinct treat detection and association with previous frames, one thing we utilize here is computing the vegetation health in real time of the trees. So specifically, as it is used for monitoring basically the vegetation health, we use this information to locate trees. And basically what we do is that we rely on the high reflectance feature of the near infrared radiation from the healthy vegetation. As you can see from the sketch on the left-hand side, different health states of the leaves lead to different levels of absorption and reflectors of radiation. So in that sense, it's easy to distinct vegetation using, for example, in that case of ours, a modality of near infrared. So by using the NDVI information in the tree association algorithm, we could also distinct and associate previous matches of the trees and along with new locations in space. Additionally, given on that we have already the tree association method, one of the things that we integrate in that sense is another based on our work, also previous work, that is building on an agricultural LOAM algorithm that has been presented also in a journal, in the Computer and Electronics Agriculture journal. So in that sense, as a brief overview of this LOAM algorithm is one of the utilizations is that it was really designed for unstructured agricultural environments. And one of the things that it was really distinct given its robustness and accuracy is that the proposed framework was consisting by two main components that incorporating motion stability during the robot traversing the field, but also map consistency during basically the traverse in the field in order to be able to understand when we were needed to do a map update and or discarding current LiDAR capture. So prioritizing incremental consistency of the map and rejecting motion distorted points of sparse dynamic objects, it actually led to higher accuracy in odometry estimated from basically from the previous scan matching against the map. So proceeding now to the evaluation of the 3D vine detection. First of all, we evaluate our method in two unmapped, fully unmapped, and vineyards in the Gallo fields. We evaluate our system under two scenarios. First is a single row, and second is dual row detection. And specifically, we selected post-noon hours in order to have some increased variability, sunlight variability in the field. As you can see here from the photos, among the different modalities, you can see that there is some diverse. So we wanted some basically separation, some distinct rows and also features that our backbone, we could test out our backbone detector. So this is why we had this assessment. So given that and how we integrate our method and given also the previous and already based works that I described is that we integrate basically the tree association framework in order to on the go associate tree trunks and with previously matched trees. But also in the agricultural loam algorithm, we included information from the additional modalities that we are receiving while on the go during the registration step. So we could also generate sparse maps in real time that contain not only the structural information from the field, but also the diverse model information. Here you can see from the photo and also from the panoramic shots from the assessments how we can showcase a thermal sparse map and with a higher thermal information on the right hand side or the left hand side. So here we have also the results from the 3D vine trunk detection. In general, basically, starting from the single row scenario, our system achieved high detection recall by having Euclidean distance error below 32 centimeters when detecting the vine trunks. Also seen in figures, basically from the figure, the left figure, 8 out of 10 trees were detected just by a single pass of our robot. As it basically as a detection part, it minimized false negative trunk detections on basically on the go. Also, I'm presenting. Also, we have the stats of the experiments. In the dual row vine scenario, we performed basically the method performed stable despite the sunlight variability. That was an important aspect of this method, and utilizing the the different modalities. Specifically, our system maintained an L2 error of below 37 centimeters with a high recall rate. And if we can summarize in overall, our system was able to detect just in this evaluation more than 70% of the examined trees or basically available trees in the field just by a single pass, but also scoring a low localization error that was low below 37 centimeters, as you can see also from the figures. So I'm not sure in time. So yeah, from that I can also maybe conclude with our work. I was Dimitris, and this was our work with an annotation-to-detection framework that we presented in NICRA in order to train a robust multi-modal detector in the field. Main features of our work, features from our work was the lightweight model of it starting from limited data. So it's a annotation detection pipeline that is can work from multi-modal detection in the field. and also diverse field settings. We demonstrate accurate vine trunk detection, and we want in future to apply it in different type of detection in the field. But also our method is autonomous ready. It can be deployed on agricultural vehicles, and we will be releasing also its method online soon. Feel free to get the links there or connect with me. And thank you so much. And thank you so much once again for the opportunity.